In this video, we're going to be continuing exercise 12.13, where we're exploring the idea of retrosynthesis, of starting by looking at the product and working backwards. So for example, here in E, we have an alcohol. And we notice that that's what's different from the starting material. We have this OH here. So what do we need? How do we know how to make an alcohol? We could make this alcohol if we had, and so I'm going to draw this retrosynthetic arrow with the two lines and the one big head. So we can make that if we had, that's what that retrosynthetic arrow means. And the way that we know how to make alcohols is from alkenes. If you do hydrations, you can either add H and OH to an alkene, and that would give you an alcohol. If you try to add H and OH to an alkyne, it would give you an alcohol at first, but it would be an enol, and it would quickly keto-enol tautomerize to either an aldehyde or a ketone. But you can make an alcohol from an alkene. We'll worry about the specific details of that in a second, but we know that if we had that alkene, we could make this alcohol. That's one way we know how to make an alkene. Well, how can we make an that's one way we know how to make an alcohol, which is a molecule that has this OH on it. How can we make this alkene, though? What do you need in order to create that alkene? Well, what's unique about it is the pi bond. So we could make a molecule with the pi bond if we had a leaving group. After all, the way you make pi bonds is with elimination reactions. And so if we had a leaving group, so like a bromine or a chlorine or an iodine there, then we could do an elimination reaction and create this alkene. We'll worry about the specific recipe for that in a second, but we just know that that is a thing that is possible. Okay, well, let's try to connect this to our original molecule. How can we create a haloalkane? How can we put a halogen on an alkane? Well, we could make that, we could make that haloalkane if we just have this alkane to begin with. We can do a radical reaction. If we have this, we could make it from, if you want this haloalkane, you could make it from this molecule by doing a radical reaction. So this is a sort of conceptual flowchart, very rough draft, no specifics here, but at least a sort of connection between different structures that lets us frame this multi-step synthesis. So now let's turn these retrosynthetic arrows around and think about the specific reactions we need to do. Start at the beginning. If we take this alkane to add a haloalkane on the most substituted position, you would just have to do a radical reaction. So you could either use Br2 in the presence of light, remember that's H nu, or you could use N-bromosuccinimide, NBS, in the presence of light, that's H nu. Either one of those would put a bromine on the more substituted carbon. Okay, next. How can we turn that haloalkane into this alkene? So we know we have to do an elimination reaction, but we have this carbon with the leaving group on is the alpha carbon, and we have different beta carbons. Now we have 3 beta carbons, but if you'll notice, the molecule is symmetrical down the middle there, and so these 2 beta carbons really amount to the same thing. All you have to do is flip this molecule over like a pancake, and those will switch places. So I'm just going to look at one of those, because of the symmetry, they end up giving you the same product. So notice, we could technically get 2 separate products here. We could form a pi bond to the beta carbon on the left, or we could form a pi bond to the beta carbon going up and to the right. We want the one going up and to the right. Okay, so let's think about the difference between these. On the left, the carbons in the double bond are bonded to 1, 2, 3, 4 carbons. That is tetrasubstituted. The other alkene, the carbons in the double bonds, are just bonded to 1, 2 carbon chains. And so that is di-substituted. The less substituted product is the Hofmann product, and the more substituted product is the Zaitsev product. Technically more stable because of hyperconjugation, but you can get the Hofmann product as your major product if you use a bulky base, like potassium tert butoxide, TBU, OK. You'll remember that the tert butyl group looks like that. You can have an oxygen on it with a negative charge that's stabilized by a positive potassium. So that's potassium tert butoxide. Now the tail of that base is so bulky that when it tries to steal a beta hydrogen, and remember that's how these reactions happen, there's a hydrogen on this beta on these beta positions that a base can steal. This is so bulky that it steals the hydrogen on the less crowded carbon, and so it gives you a pi bond in the direction of that less crowded carbon. So we can get that Hofmann product by using a bulky base like potassium tert butoxide. Once we have that, now we can rearrange our other arrow, reverse the retrosynthetic arrow. Now we just have to add this OH on. Now notice we have 2 carbons in this double bond. One carbon is bonded to 1, 2, 3 other carbons, so it is tertiary. Another carbon is just bonded to 1, so it is primary. We want the OH to go on the less substituted carbon. And notice there's an H that added here, because there's no H here, but there is an H in the products. We want the H to go to the more substituted carbon. If a hydrogen is added to the more substituted carbon, that is anti-Markovnikov addition. So we only know one way of adding H and OH, anti-Markovnikov. That is hydroboration oxidation. So in the first step, you would use BH3 stabilized by THF, tetrahydrofuran. So this is borane stabilized by tetrahydrofuran. And then in the second step, or in the first step, you could also use 9-BBN. It's a solid, so it's easier to work with. This is a gas. Both of the boron compounds are toxic. In the second step, you'd use hydrogen peroxide followed by sodium hydroxide. And that hydroboration oxidation would add the OH onto the less substituted carbon, the hydrogen onto the more substituted carbon. So overall, thinking backwards, we were able to develop a recipe for creating this transformation. The first step was doing a radical reaction. So for example, adding N-bromosuccinimide and light. And if we were thinking forwards, that would have made sense because we have an alkane. You can only do 2 things with an alkane. You can light it on fire and turn it into carbon dioxide, water, and heat, or you can do a radical reaction, and that's what we did here. That opens up elimination reactions, substitution reactions, and once you do an elimination, it opens up addition reactions, as we see in this problem. Once you have that haloalkane, you can do an elimination reaction. We wanted to get the Hofmann product, so we used a bulky base like potassium tert butoxide. And once we have that alkene, we wanted to add the OH on the less substituted position and a hydrogen on the more substituted position. That's anti-Markovnikov addition of H and OH. That's hydroboration oxidation. In the first step, you'd use something like 9-BBN, and then in the second step of that hydroboration oxidation, you'd add hydrogen peroxide and sodium hydroxide. And so this recipe will give rise to or achieve this transformation. All right, let's try F. Now again, you could solve this forwards, but in this video, in this exercise in general, we're trying to practice the skill of retrosynthetic analysis, trying to work backwards, because you can always work either way, and it's important to be able to work both ways so that if in one direction you get stuck, so if you're working in the forward direction, you get stuck, well then you'll be able to work in the reverse direction and get yourself out of the impasse. What we see here is a carboxylic acid. We've only learned one way to make a carboxylic acid, and it was through ozonolysis of an alkyne. So the giveaway for that was the carboxylic acid. so far in Organic Chemistry 1, that's the only way we've learned to make a carboxylic acid was through ozonolysis of an alkyne. Now when you do that, you saw another carbon off of the molecule. And that makes sense because in the beginning we had 4 carbons. At the end, we only have 3. That's another hint that you had to do ozonolysis. So, in other words, we could make this molecule. We could make this if we had, I'll draw that retrosynthetic arrow, that means if we had 4 carbons. So, instead of all these oxygens that come from the ozone, if we had 4 carbons, oops, and an alkyne on the end. Oops, I added too many there. Sorry about that. This one. So here, if you count them up to make sure, you've got 1, 2, 3, 4 carbons. So 1, 2, 3. So we just added that extra one at the end. And the third carbon that has the carboxylic acid on it, notice that that was one of the carbons in the triple bond. Okay, so we could make this if we had this alkyne by doing an ozonolysis. But how can we make that alkyne? Well, look at the original molecule we have. We could make it from a geminal dihalide. We would just have to do elimination reactions. And that's it. So let's turn these retrosynthetic arrows around and think about the specific recipes we'd have to use. We have 2 leaving groups. That means we can create 2 pi bonds by doing 2 elimination reactions. We would just have to add excess sodium amide. That would not only create the 2 pi bonds, but even after it created it, there's a hydrogen here that this base would steal. And so there would be this unstable carbon with a negative charge. So in the second step, you just want to do a water wash so that this will steal a hydrogen from water and go back to being stable. So that's how we can make that. And then once we have that molecule, we could make this carboxylic acid by doing an ozonolysis. Now when you do an ozonolysis on an alkyne, the first step, as always with an ozonolysis, is ozone. So you're breaking a molecule apart by adding ozone. That's O3. But in the second step, if you do ozonolysis on an alkyne, the second step is H2O. Compare that with if you do ozonolysis on an alkene, where the second step is DMS. So with an alkyne, it's H2O. And what ends up happening is you cleave that bond. The carbon attached to the chain still turns into a carboxylic acid. And the other carbon, here carbon 4, would bubble away as carbon dioxide. So that ends up being another product, but it's a product whose story is different from the carbon molecule we're interested in. Who knows what will happen to the carbon dioxide that bubbles away? It could get released into the air, incorporated into a tree. The leaf then falls from the tree, decays into the ground, sinks into the dirt, gets buried over time, sinks into the mantle of the earth, gets compressed into a diamond. Who knows what will happen to that carbon dioxide, the sagas and adventures it will go on. But for us, we're interested in this particular adventure here. And for us, it ends at the carboxylic acid. So we found in this exercise, we used a quick retrosynthetic analysis to devise a recipe for this transformation. Starting with our geminal dihalide, this carbon chain that has 2 halogens bonded to the same carbon, geminal, twins, we would add excess sodium amide to do 2 elimination reactions to create 2 pi bonds, and we follow it up with a water wash just to stabilize the carbon on the end there. Once we have that terminal alkyne, we can do the ozonolysis to get the carboxylic acid. The first step in the ozonolysis is bubbling ozone through our solution, and the second step will be another water wash. So these 4 steps would achieve this transformation. Okay, How about G? So again, you could solve this exercise in the forward direction, but just to sharpen our retrosynthetic skills, we're going to work in the reverse direction here. So we see our product. We could make that if we had, so this is our retrosynthetic arrow, we could make this if only we had this other molecule. So we're thinking backwards. What do we need? Well, you definitely need that carbon chain. And if you notice, a Br and an OH in opposite directions, one's going away, one's coming toward us, that's a halohydrin. We learned how to make those from alkenes, halohydrins. So if you had a double bond here, then you'd be able to make that halohydrin. Okay. Well, can we make this in one step from this alkyne? No. But one of the differences we notice is that this has 2 carbons and this has way more. So what we can do first, just to make it resemble this a little bit more, is to turn it into an alkyne. We could make this from an alkyne. So if we had, and here, the number of carbons we have is 1, 2, 3, 4, 5, and 6. So if we take this molecule, we're just trying to get it to resemble this a little bit more. So if we add another pi bond there between carbons 3 and 4, and then I just want to make these linear, so there's our triple bond. So if we have that, and notice it's 1, 2, 3, 4, 5, and 6. So if we had this triple bond, which resembles our starting material a little bit more, we'd be able to make this, for sure. We could either use H2 and Lindlar's catalyst or dissolving metal reduction. Okay, well, do we know a way to make this in one step from our starting material? No. But we could make it in a few steps. Because the only difference between this molecule and our final molecule are the number of carbons, and we know that to add carbons onto a molecule, there's just one method for us that we know in organic chemistry, one. And that's to use a terminal alkyne and an alkyl halide. So, if we take the molecule that we have, but we remove one of the carbon chains from it, so let's say carbons number 1 and 2, and we replace, so now what's left is a terminal alkyne, then we'll be able to take those other 2 carbons, add those as an alkyl halide, and make the product that we have below. Okay. Let's try just one more step. One more step, and let me just clean this up a little bit. Okay. Well, we could make that, if you notice, if you're comparing this molecule and the molecule that we have here at this point, it's this other chain that's added. That's the only difference. And we could make that from this starting material by doing the same sort of reaction, by adding another carbon chain with an alkyl halide. So this is a sort of general flowchart, a sort of general draft of how these could connect. And we drafted it going backwards using retrosynthesis with these retrosynthetic arrows that mean you could make this from this other thing. Okay, well now that we have this, we can reverse our arrows and come up with the specific recipes. The first thing we have to do to add a carbon onto the chain is to use a strong base, and here we're just going to use one equivalent, so of sodium amide. That will rip off this hydrogen at the end and turn that into a carbon nucleophile. Then we can take the number of carbons we want to add, so here it's these 2, oops, and we can make those an alkyl halide. So that if we use the base to steal the hydrogen there, turn that into a nucleophile, that could attack this carbon here, kick off the leaving group in an SN2 reaction, and that would leave us with our product. So that's our first two steps. Okay, next, let's look at the next retrosynthetic arrow. Reverse it. If you look at the differences here, it's what's on this side of the triple bond. We've added another ethyl group. And so the procedure is going to be the same. Actually, the same exact steps. So in the first step, we would use excess sodium amide to rip the hydrogen off there, turn that into a carbon nucleophile, and then that could do an SN2 reaction with this carbon chain. It would attack this carbon here, kick the leaving group off, and you would form this new bond between the terminal alkyne and the two carbons. And so you'd add this carbon chain onto that terminal carbon. Okay, next. Once you have the alkyne, you could turn it into, and notice this is a trans alkene. If you draw a line down the long end of the double bond, you could see that the two carbon chains are going in opposite directions of that line. One's pointing kind of to the left, the other one to the right. So this is trans. To get the trans alkene, you have to add solid sodium and liquid ammonia. That's dissolving metal reduction. And then once you have that, you can add the H and the OH and the Br, the halohydrin, by adding Br2 and H2O. So by thinking backwards, we were able to come up with this recipe to achieve this transformation. First, we would need to add carbons to one side of that ethyne molecule, more commonly called acetylene. It's the gas that's burned in welding torches. So to do that, you would treat it with one equivalent of sodium amide. That would rip hydrogen off the end, turn this carbon into a nucleophile, and then in the second step, you'd look at how many carbons you want to add. You want to add 2, and you'd add a halogen or a leaving group onto that, so it can do the SN2 reaction and make the new bond. Then, seeing the change you want to make next, you want to add 2 more carbons. It's the same procedure. Use sodium amide, and here, because we only have one place where you could rip the hydrogen off, it doesn't matter if you use just one equivalent or not. So you add that, it rips that hydrogen off, that turns into a nucleophile, and again, you provide an alkyl halide with the right number of carbons, here 2, and a leaving group so it can do the SN2 reaction. That gives us our alkyne. We can turn that into the transalkene by doing dissolving metal reduction, so solid sodium and liquid ammonia. And then once you have that, you can turn it into the halohydrin, a molecule that has a Br and an OH right next to each other, by adding Br2 and H2O. So this recipe would achieve this transformation. Okay, last but not least, H. So again, we're going to work backwards. Here we have an alkyne. How do we know to make an alkyne? We could make an alkyne from any dihaloalkane. We just do 2 elimination reactions. So if we had an alkane with 2 halogens, and it wouldn't really matter where they are, except they would have to be on one of the 2 carbons that where the triple bond is. Well, then we could create the alkyne. So in that case, if we wanted to make that, how could we make that? Well, that would be a little difficult to make. We'd actually have to have a triple bond in the first place to make this. So let's think about something we could make with just a double bond. That would be a vicinal dihalide. Any dihalide can be used to make an alkyne, or I should say a geminal or a vicinal dihalide could be used to make an alkyne, because you have 2 leaving groups. That allows you to make 2 pi bonds, one for each elimination you would do with each leaving group. So if we have those on neighboring carbons, we could make that from an alkene. If you had this double bond here, if you had a double bond here, then you could make that dihalide. How do you make an alkene? Usually you make a pi bond like that from an elimination reaction. So if we had just one bromine, we'd be able to do an elimination to create that. Now, we can't make that bromine from our starting material. We can't add a bromine there in our starting material. So, but we can add a bromine on this on the most substituted position using a radical reaction. So we can connect this back to that. If you had a pi bond here, you could connect that back to having a halogen on the most substituted position, and that you could make from your original alkane. Okay, well, this definitely looks like a lot. Let's walk through this in the forward direction, see if it becomes a little clearer that way. We have an alkane. There are only two reactions you can do with an alkane. You could light it on fire and get carbon dioxide, water, and heat, or you can do a radical reaction. I'm going to use NBS and light, H-nu. You could also use Br2 and H-nu, ultraviolet light. That puts a bromine on the most substituted carbon in the molecule, the place where the most stable radical would form. So that's how we can get that. Then we want to do an elimination reaction. Now, we want to get the most substituted possible alkene. Notice you could form an alkene to the top left, but that would be disubstituted, to the bottom left, but that would be disubstituted, or to the right, which is trisubstituted. That's the most substituted, that's the one we want to get. That's the Zaitsev product. To get the Zaitsev product, use a skinny base like sodium ethoxide. Oops. Once you have that alkene, you can add a bromine onto the less substituted carbon and a hydrogen onto the more substituted carbon by doing hydrohalogenation. But because the hydrogen went to the more substituted carbon, it's anti-Markovnikov addition, and you would want to add a peroxide. Okay, once you have the bromine on there, you can do another elimination reaction. Now again, you could form a pi bond in two directions. You could form it to the left. That would give you a tri-substituted alkene, or you could form it to the right, where you have just a mono-substituted alkene. We want the mono-substituted alkene. That's the less substituted product. That's the Hofmann product. You make the Hofmann product using a bulky base like potassium tert butoxide. Okay. Once you have this final product, you can add two bromines on it like this by just adding Br2. And once you have Br2, that vicinal dihalide, you can turn it into an alkyne by doing two successive eliminations. So that's first excess strong base sodium amide. That would not only do the two eliminations, but also rip the hydrogen off of here and turn this into a carb anion, a carbon with a full negative charge. So to stabilize that, you just do a water wash. So in this one, I didn't spend a lot of time on the details of the reactions because we've spent so much time on that before. In this very last one, I just wanted to walk through the sort of flow of thought that you can use to achieve these long multi-step syntheses like this. So by first thinking backwards and then going forwards and filling in the specific reactants, we were able to come up with a recipe to achieve this transformation. The first thing you would want to do is some sort of a radical reaction. Here we used N-bromosuccinimide and light. You could have also used Br2 and light. That added a bromine onto the most substituted carbon. Then we wanted to get the most substituted alkene in an elimination reaction. We wanted to get the Zaitsev product, so we added a skinny base. Here I added sodium methoxide, but it could have just as well been sodium hydroxide or sodium methoxide. Then onto that alkene, because we're trying to walk the electron density to the right of the molecule, so we do successive additions and eliminations. We want to make the reactive part of the molecule further to the right, so we want a bromine, a leaving group, to add to the less substituted position, and a hydrogen to go to the more substituted position, so that was anti-Markovnikov addition of H and Br. So we hydrohalogenation in the presence of peroxides. Now again, we want to walk the electron density to the right, so we wanted to get the less substituted alkene in an elimination reaction. That means we wanted to get the Hofmann product, so we used a bulky base, like potassium tert butoxide. Once we had that, we were able to make our dihalide, our vicinal dihalide, by adding Br2. And those bromines would have added anti to each other. And once we have those two leaving groups on our molecule, we could do two elimination reactions to create two pi bonds, the two pi bonds in the alkyne. And we would make that by treating this dihalide, that vicinal dihalide, with first excess strong base, excess sodium amide, that would do the eliminations, create the two pi bonds, but it would also rip the hydrogen here off of the alkyne and turn this into an anion, which is unstable. So to stabilize that, we shake it up with some water, and the water does a proton transfer and puts the hydrogen back on. So overall, this recipe would achieve this transformation. So in this exercise, we saw how you can solve these are nonlinear problems. You could work forwards, but you could also work backwards. So if you ever get stuck going in one direction, try going in the other one. You can use the retrosynthetic arrows if you want to, just to sort of make an outline, and then follow up with the specific recipes after you start making connections. And that's retrosynthetic analysis.